Section 2.5. Today we're looking at implicit differentiation. Differentiation, that word differentiation means finding a derivative. Okay? So we're talking about finding a derivative in a very different way than what we've done before. So let me talk first about what we've done so far. What we've done is actually called explicit differentiation. We don't usually put that word on there because it's the one we start with and we're doing it explicitly. It means you're taking a derivative of y in terms of x when you can take the equation and you can write it as y equals. In fact, you don't even have to take it and write it that way. It starts that way, typically speaking. So when it starts with y equals on one side of the equation, you could have all the x's on the other side. You can take it, the derivative, with all the rules that we've done so far. Okay? However, sometimes there are equations. For example, if you have the equation for a circle, like it's possible to take the equation for a circle, which is like x squared plus y squared equals r squared, and you can solve it for x or for y. I mean, like that's possible, but it's not very pretty, and especially if you end up with something where it's not centered at the origin. It's not super easy to solve that for y, and sometimes there are equations that are simply not even possible to solve for y. And when that happens, we do the derivatives using implicit differentiation. So this is taking a derivative of y in terms of x when an equation cannot be simplified with y equals on one side of the equation and all the x's on the other side. In order to use this method, what we do is we treat x and y both as variables, and then all the derivative rules that we've already used, we keep using those rules. So there's no new rules, they're just being used in a different way. Okay? So the first one that I'm giving you an example of, it's not an equation of a circle, but does anybody know what that's an equation of? It's similar to the equation for a circle. It's not an ellipse, but you're so close. It's a hyperbola. Yeah, this is an equation of hyperbola. If you don't know what that is, it doesn't really matter. Just kind of throwing that out there. It's for free. You got that as bonus today. We could solve this for y. Agreed? The messy thing about solving this for y, of course, though, is that we'd have to split it into two equations because when we take the square root, we'd have to have the positive value, we'd have to have the negative value, and so we'd have, pluses or minuses in there or something like that, which would be kind of messy. But working with this implicitly is actually very clean. So let me show you how that works. The first part you already know. What's the derivative of x squared? 2x, no problem. Now, just for a moment, we're going to pretend like y is any other variable, x's and t's and s's and all the things that we've done in the last section of material. What would the derivative of y squared be? Yeah, there's a negative there, so it's negative 2y. The kicker is that we are actually treating y still as a function of x. So every time we take the derivative of y, which we just did, we're going to write dy dx. And remember that's, in fact, I don't even know if I've said that yet. Let me write it in here because I don't know if I have. This notation, y prime of x, can also be written as dy dx. Have I shown you guys that yet? The Success Center has? Okay. It's like, I don't think that I have actually this semester. I don't think it shows up yet in our book showing up like this. Dy dx is a little bit better for what we're working with here than writing it as y prime. And the reason is because those little primes tend to sort of disappear because they aren't very big. They don't make a big, impact on your paper, and so it's really easy to lose one, and then things go awry very quickly. So if we write dy dx, you're not going to be tempted to think, oh, that's just y, okay? Dy dx, that notation means the derivative of y, and then on the bottom means with respect to x. So that's why that's kind of showing up there. It's also very nice because if you remember your equation for slope, which is what a derivative is, it's the change in y over the change in x. And you can see the notation showing up in a very similar way. dy on top and dx on bottom. All right, let's finish this guy up. What's the derivative of 25? 0. Okay, and what we do, to solve this equation is we actually get the dy dx by itself. So we are, in the end, going to solve for something. We're not going to do it at the beginning. So the first thing I can do is I can move my 2x. So this is negative 2y. Dy dx equals negative 2x. And then what would I do to move the negative 2y? I can't add it. I would divide by it. The reason I can't add it is because these two are understood to be multiplied because they're next to each other, so we would want to divide to get it moved, yeah. So divide by negative 2y. Do you have a question, Jeff?
dy dx is like another variable?
dy dx is the same as y prime. Yeah, this is just y prime. It's just an alternate way of writing y prime, that's all it is. If you really, really, really want to write y prime everywhere that I put dy dx as you can. I just think that it's easier to lose the prime and then mess things up later, so I tend to not use it that way. This very nicely cleans up to x over y. Now, let me just show you real quick what would happen if we tried to actually do this with explicit differentiation. First of all, the answer would look different at the end, but the first thing I'd actually have to do is to solve for y. So I'd start out getting here that y equals, it's plus or minus the square root. It would end up being x squared minus 25. And the derivative would involve the chain rule, right? Well, if you'll notice, what we didn't involve any kind of chain rules or product rules. There was a chain rule. I didn't mention it exactly. You kind of glossed over it. But the derivatives that we used were actually a lot easier than using the derivatives that would be required if I solved this particular one for y. It's doable that way. You could do it. It wouldn't look quite the same at the end. The reason it wouldn't look the same at the end is because you'll notice right here I still have a y in my right-hand side of it, right? And the one at the top, if I changed it like that, I wouldn't have y in it on the right-hand side. So it will look different, but it'd be an equivalent answer. It'd just be actually harder to work with. But it's not always even possible to solve for y. And the second one is an example of one where I even if I wanted to, I cannot solve this for y. Can you see why? There's y's in two locations, right? So on this one, I only had y squared, and I'd have the ability to isolate the y squared and then take a square root. And I have a plus or minus, which isn't friendly, but it's possible. Over here, because I've got y's in two locations, I wouldn't even be able to do this if I wanted to. Now, this is kind of messy because I've got division on one part of the equation, okay? So I tend to not like to work with things that are messy. If I can make them cleaner, I try to do that. And this one's actually able to be made cleaner pretty quickly, and what we can actually do to do that is to multiply by y on both sides. So that's the first thing I'm going to do, just so that I don't have any division involved. X plus 3 is a lot easier to take a derivative of than x plus 3 over y, right? I do end up with 4xy here, so that's a little messier, but still not as bad. And y cubed, which is just as easy as y squared. Okay? If you don't do this, that's fine. Your answer will look different. It will be equivalent, and it'd be okay. You're just going to have a little bit more work involved if you do the quotient rule on the left-hand side instead. So let's take a look at finding the derivative of this. The only part that will look different than what we've done is the parts that have the y's in it, okay? Everything else looks the same. So what's the derivative of x? 1. And what's the derivative of 3? 0. So this is 1 plus 0, or just 1 on the left-hand side. Okay, so we have two pieces over here. I'll circle the first one in red. 4xy. X is a variable and y is a variable, right? Yeah. And they're multiplied, right? So when we multiply two pieces that have variables in it, we have to use what rule? The product rule. There's a product rule here, okay? So with the product rule, I have two pieces. I'm going to mark them separately. 4x is one of my pieces of my product, and y is the other piece of my product. So with the product rule, the first thing we do is simply write down 4x. Write down the first piece. And then I need to know, what is the derivative of y? Well, the derivative of y is 1, but then anytime I take the derivative of y, it's actually y prime, right? Every time you took the derivative of f of x, you wrote f prime of x. Agreed? So the derivative of y is 1 and then y prime, or dy dx. So this is dy dx. So write yourself a note somewhere so that you remember. This sounds kind of funny, and it almost looks like you're writing itself funny even. The derivative of y is y prime, or dy dx. That's what it means. When you take the derivative of y, It's dy dx. Okay? Even in the middle of a product. Now we're going to go the other direction here. I'm going to put a plus sign. What's the derivative of the 4x? Which is 4. And then the second piece, y, I simply write it down as y. And all of this is the derivative of 4xy. Okay? Now we've done a piece that looks like y cubed. We did y squared on the previous screen. So with y cubed, what would the derivative of y cubed be?
3y squared.
Yep, we're going to get the 3y squared. But then anytime I take the derivative of something with y in it, I have to include dy dx. So it's 3y squared dy dx. And I mentioned it on the previous screen. I didn't actually go back in detail and show you where it was, but that's where the chain rule is. The derivative of the outer part, the cubing, is the bring the 3 down, put the power 2. But then the derivative of y, what's actually inside of my cubing function, is dy dx. That's a chain rule. It's not quite like looking like the chain rules we did before, but it is a chain rule. All right, what you see here is you see 2 locations that have a dy dx, right? So implicit differentiation is never over until you have written down dy dx equals, and there's no dy dx's on the other side. All right? So I have 2 pieces that have dy dx in it, and I actually have one piece on the right-hand side that doesn't have a dy dx in it, right? So the one piece that doesn't have a dy dx, the 4y, it needs to shift over to the other side. It needs to move. So the very first thing I need to do is I need to subtract that 4y to the left. So 1 minus 4y is on the left. And I have 4x dy dx plus 3y squared dy dx. You might be looking at this and thinking, okay, when we started the first of this problem, you told me the reason I can't solve this for y was because y was in 2 places. And I said that, right? You did. And now you're telling me I need to solve this for dy dx, but the dy dx is in 2 places. And it is. Okay, is everybody tracking with me on that? The difference is that the original y that we couldn't solve for had y in one location and it had y cubed in the other location. Or it had y in a denominator and it had y squared not in a denominator. Okay, depending on which line of my work you're looking at. The y's were different. They weren't identically the same. The difference here is that dy dx is identically the same. One of them's not squared and the other one's original. I mean, it's not like that. They're identically the same. And the reason that matters is because that means that dy dx could be factored out. Right? Good old algebra comes to the rescue. So I can actually write the dy dx here and factor it out so that I have 4x plus 3y squared as the other factor. Okay, is that all right? You don't have to like it, but do you understand the ability to factor it out? Okay? So then we just divide by the parts in parentheses. You got it. So we have 4x plus 3y squared that we will divide both sides by. So if I write it with the dy dx on the left, then dy dx will equal 1 minus 4y divided by 4x plus 3y squared. What do you think? It's kind of cool. It cleans up, and it actually ends up being pretty direct in terms of the algebra at the end. And it always has that feeling of being able to have dy dx factored out with a bunch of other stuff that you couldn't. So let's try another one. This one, again, you could solve it for y squared. I mean, like, it physically is possible here. There's only one of them. You'd end up with a plus or minus. You're going to have some messy quotient rules and chain rules involved if you try. And honestly, the directions told you to do it differently, so that's not the point anyway, right? Told you to do it implicitly. So we're going to take a look at this from an implicit perspective. The first piece has 4x squared y squared, which means there's a product, right? Right? This is yes. Okay, cool. So I'm going to just draw that line between there so that we can see each piece of the product separately. I have x squared and I have y squared. So product rule says I do the first piece and just write it down. It's x squared. And then what's the derivative of y squared? 2y dy dx. Good job on remembering the dy dx. You okay, Nick? Okay, fantastic. Halfway done with the product rule. The other piece is the easier piece. What's the derivative of x squared? 2x. And then I write down y squared. All right, derivative of 37, 0, equals the derivative of 4x, 4. This one's actually friendlier than the last problem. Why? There's only one dy dx. So I'm going to do some algebra to shift some things around. I'm going to move my 2xy squared to the other side with subtraction. So x squared, 2y dy dx equals, and I had 4 minus 2xy. Then what? Divide by x squared 2y. Yes, thank you. I left that square off. Appreciate it. And then divide by x squared 2y. There is one thing that can be cleaned up on the right-hand side. Did anybody see it? I can't take out an x and a y because there's 3 terms. There's because of subtraction, and not all 3 terms have an x or a y in them to eliminate it. There's a 2. Yeah, there actually is a factor of 2, however, in all of them. So here's my 4 is divisible by 2, the 2 is divisible by 2, and the 2 is divisible by 2. So I can divide everything by 2. So I actually will have 2 minus xy squared over x squared y. Kaylee, it is possible that you could end up with a variable canceling out, though, too. It will happen. So it's not an unheard of kind of thing or anything like that. This one just didn't happen to have that. All right, we're going to pause there for today. I have a few problems, obviously, left. And it means that we clearly can't have a quiz over this on Monday. So your quiz will be pushed to Tuesday, or Wednesday, not Tuesday. I'm not going to make you come in on Tuesday. So we'll finish this 2.5 up on Monday, and we'll move into 2.6 as well. The homework will shift to Wednesday as well. Yes.